Welcome. We're going to continue exploring each of those laws that I mentioned during the introductory video. The first one, obviously, on the list is the ideal gas law. And that's pretty much the equation I showed you that we're going to start with. And then each of those equations can be algebraically converted into multiple other forms that can be explored, right? So without further ado, let's get started. Now, there's a special condition that we must talk when we talk about gas laws, okay? And that is standard temperature and pressure. You do not have to memorize this because it will be in the appendix section. As I said, a great deal of information throughout this course will be constant, so it will be in the appendix. You do not have to memorize. Standard temperature and pressure is either 0 degrees, or if you add 0 to 273, you get 273 Kelvin and 1 atmosphere, okay? And then 1 mole of any gas, irrespective of the identity of the gas, 1 mole of any gas at STP occupies 22.4 liters. Again, this is a statement, a constant, which you do not have to memorize. But you must understand that it's 1 mole of any gas, not 1 gram of any gas. Okay, it's 1 mole of any gas at STP occupies 22.4 liter. This means you may have to put in different mass of each of the gases to achieve the 22.4 liters. Now, if you see this visual, we got 3 cylinders containing 3 different gases: helium, xenon, and methane. Each of them have been pushed into a balloon and blown to the same size. Each of those balloons are 22.4 liter, provided each of those balloon contains 1 mole of each of those gases at STP. This does not, there's 2 things. First, each of those gas must be 1 mole, and the temperature and pressure must be either 0 degree, 273 Kelvin, and 1 atmosphere. That's STP. If these 2 conditions are met, then the balloon will be of same volume, which will be 22.4 liter. Now, on the other flip hand, I could easily convert this question into something that you already know. If 1 mole of each of these gas at STP occupies 22.4 liter, what does that in terms of mass? What does it mean in terms of mass? Well, we know 1 mole of HE is, well, 1 mole over 1, and helium is 4 grams over 1 mole. Sorry, 4 grams over 1 mole. So that'll be 4 grams, right? 1 mole of xenon is 131 grams per mole. So 1 mole over 1, 131 grams over 1 mole, and that'll be 131 grams. Methane is 16 grams, so 1 mole over 1, 16 grams over, that's the molar mass of each of these gases, right? 16 grams. So essentially, at STP condition, which is standard temperature and pressure, if you put 4 grams of helium, 131 grams of xenon, and 16 grams of methane into a balloon, assuming we're treating these gases in masses, then you would achieve this perfect balloon sizes that are equally the same. Do you see that? Okay, so the 2 things I do want you to remember, not remember as in memorize because it will be in the appendix section, but I want you to understand STP is a special case, standard temperature and pressure, okay? And then this is another statement that's a constant. 1 mole of any gas at STP occupies 22.4 liter. If you don't remember these 2 things, then chances are you're going to struggle with the calculations. So without further delay, let's actually do this problem. Okay, now ideal gas law is one case where Pressure must be always expressed in ATM. Temperature must be in Kelvin. Volume must be in liter. And or, remember I said you have to use the bottom value when it is, this is the unit for this. Okay. This is the unit for, you use this value because remember the ideal gas law is PV equals nRT, right? In all other cases, temperature must be in Kelvin. The pressure and volume does not have to be converted to ATM. But whenever we are dealing with ideal gas law, all of this must be met. Otherwise, chances are your problem is not going to work out. So this question is asking, if I have an unknown quantity of gas at a pressure of 1.2 ATM, a volume of 31 liters, and a temperature of 87, how many moles does that correspond to? Well, pressure is already given in ATM, so that's good. If not, you must convert it. Volume is also given in liters, which you do not have to convert. Temperature is given in Celsius, which means we must convert that to Kelvin. So it's 273 plus 87. That's 360 Kelvin. And then R value is constant, is 0.0821. All you got to do is put it in this expression. So it's 1.2 times 31. Again, I'm not writing the units here for space constraints, but you can do that. So times 360. And you solve for n, that is, you divide the one, you multiply 1.2 times 31 and you divide that by 0.0821, and then you divide that by 360. So that's 1.25 moles. So the thing here is, again, this law, this equation will be in the appendix. So you do not have to memorize this equation, but it's important when you're handling, well, when the question is, when do I use it? Well, basically, you'll be given four things or three things plus the gas constant, and you'll be asked to find one of this. Then automatically you have to use the ideal gas law. Okay, good. So that's how you do this. Make sure all of these are in appropriate units before you plug it in. Okay. In all other cases except ideal gas law, temperature alone must be converted. The pressure and volume don't have to be converted. Okay. If you want to know why that is, just ask me in class. For now, I'm just going to skip and go on to the actual problem. So determine the volume of CO2. I should have said volume occupied by 2.34 grams of CO2 at STP. So right away, we need to know, we have to find volume, right? And STP means it's STP is 0 degrees or 273 Kelvin. Again, you do not have to memorize this, and 1 ATM. So right away, what do we know? Well, we know temperature, right? We know temperature is 273 Kelvin. We know pressure is 1 ATM, that's given. We know right away, whenever we are dealing with volume, we must use gas constant, that's 0.0821. And then we also need to find volume. So there's something else we need to know before we can actually complete this problem, right? Which is, we want to find this. We know this, we know this, we know this. We don't know n yet. When you don't know two variables in algebra, you must find a way to get one, otherwise you cannot solve the problem. Well, we do know 2.34 grams of CO2, and then that's molar mass of CO2. Remember, to go from grams to moles, we have to do grams over moles, molar mass, right? So that's 44 grams over 1 mole, which will give us 2.34 divided by 44 is 0.053 moles. So now we can plug everything in. Now you see everything is in the appropriate unit. Temperature is in Kelvin, pressure in atmosphere, R is constant, V is what we need to find, which will turn out to be in liters, N is in moles as it is. So let's plug everything in. 1 times V equals 0.053 times R is 0.0821 times T is 273. You plug all that in. So that's 1.18 liter. Now I could easily convert this question as to find it in milliliters. What if I do that? Well, right now the problem is done. This is the answer. If I want to find the answer in milliliters, which we would not, but if I can purposefully make it, then we know that 1 liter is 1,000 milliliters. I will obviously give that conversion if needed. So that's 1187 milliliters. This is not needed. This is optional. Okay, this is entirely optional. This is where the problem ends. But if you sit for standardized exams like MCAT or PCAT or whatever that is, they will ask weird things that is not needed. All right. So I got 2 more problems on ideal gas law, but I'm going to stop this video here and I'll pick it up in the next video. So stay tuned.